Good afternoon and welcome to the Non-Associative community. I'm glad to introduce the speaker of today, Bauyrzhan Sartayev from the Suleyman Demirel University. The title of his talk is Binary Perm Algebras and Alternative Algebras. Please.
Okay. Firstly, our dear organizers and the participants, thanks for invitation. Do you hear me?
Yes.
Okay, then I'll start. So today the talk is about binary perm algebras and the alternative algebras. So firstly, let me start from aim of this talk. So let me first read, of course, and then I will, in explicit form, explain every part of this aim. So firstly, we describe the defined identities of variety of binary perm algebras. Why it's interesting, because it's a variety of alternative algebras. So that's known class of algebras, and moreover, we construct the basis of free binary perm algebra. In addition, we describe subalgebra, which is obtained from binary pair algebra under commutator, which has connection with the Malcev algebras. So I will explain it later how they have a connection with each other. So let me start with the main notions. So firstly, we fix some variety of algebras A. So and we denote by A2 that is the variety of this symbol, it's called, it's sometimes we say it binary A, variety of binary A algebras. So we denote by binary A algebras, variety of algebras whose to generate a subalgebra belongs to A. So in other words, if we take any algebra from this variety, and if we take just to generate a subalgebra, then it belongs to initial fixed variety of algebra A. And in analogical way, we define A1 and we call it unary algebra. And it means that every one generated subalgebra of unary algebra belongs to A. So one of the well-studied such classes of algebras is a variety of associative algebras, which we denote by this way. So in the first work by Albertis proved that if instead of A, if you fix a variety of associative algebras, then unary associative algebra, it coincides with the variety of power associative algebra. So that this result is published here. So that's classical result. And what about binary associative algebra? So in this book, that is a book of 4 authors, rings that nearly associative, there is written that binary associative algebra, the defining identities, of course, of the variety of binary associative algebra, that is these two identities. These identities also known as identities of defining identities of alternative algebra. And we denote alternative algebra by this way. So that is a well-known result. Oh, I forgot to tell that this result about binary associative algebra, that binary associative algebra defined by these two identities, that is a result of Artin. That's the Artin theorem. And although there are have been many studied on alternative algebras, of course, the basis of free alternative algebra has not been discovered yet. So the basis of alternative algebra is unknown. Now another examples. If we take instead of a variety of Lie algebras, then it's described by Gainov. If we take instead of a Leibniz variety of Leibniz algebras, then it's described by Ismail Jumalidaev. And if we take instead of a Tsembiel, then it's also this problem solved by Ismail Mashur Smadyarov. So let me explicitly show these results. For example, In the case A is a Lie, so if it's equal to Lie, then the class of binary Lie algebras, which we denote by this way, of course, over field of characteristic different from 2, then the variety of binary Lie algebras can be defined by these two polynomials, polynomial identities. The first one is anti-commutativity, the second one is this one. So that is a Jacobian. That is the result of Gainov. And what about Leibniz algebra? So Leibniz also well-known variety of algebras. That is a generalization of variety of Lie algebras. So Leibniz identity, that is this one. It's discovered by Aladei. So let K be a field of characteristic not equal to 2, and let A be algebra over K. And for any ABC from this algebra A, we define the following bracket. So that is a if that's analogical thing as a it's not Jacobian, that's as a, let's call it Leibnizian maybe. So because that's Leibniz identity. So then in second work, there's proved that is proved by Ismailov and Jumalilayev. If A is algebra over field K, is unary Leibniz, if and only if it's satisfied to the following two identities. So these brackets are Leibnizians. And so that is the defining identities of unary Leibniz algebra. And this identity, this result also this result also proved by Gainov in approximately 2010 maybe. And what about binary Leibniz algebra? So again, if an algebra A over field K is a binary Leibniz, if only if it's satisfied to the following identities. So the main idea here, so it means that if you want to, here main problem is to find the list of defining identities of some variety, the list of defining identities of binary of the variety of binary algebras or unary as here. And what about Symbiote? What about Symbiote? That is the results solved by Ismailov, Mashurov, and Smadyarov. That is this result. Let K be a field of characteristic 0. Then an algebra A over field K is a mono symbol if only if it's satisfied to the following identities. So variety of mono symbol algebras can be defined by these two identities. And what about binary symbol? Let K be again a characteristic different from 2. An algebra A over again field K is a binary symbol if only if it's satisfied by these two identities of degree 3. So here, binary symbol is a special case. Why? Because you can see that it looks like a variety of symbol algebras for this problem. It looks like a variety of symbol associative algebras. Sorry. Why? Because as we said before, variety of associative binary of associative algebras can be defined by identities of degree 3 by two identities. And for binary Lie, here identity of degree 4, Leibniz also identity of degree. It contains the identity of degree 4, but for symbol, we as in associative case, we have only two identities in degree 3. So that is a well-known result. That is the results that related to binary, unary, and the binary algebras, variety of algebras, of course. Oh, I forgot to tell you that one remark. Free basis of the free Lie algebra is well known. That is a whole. We have a whole basis. We have Linden-Shishov word that's all basis of the free Lie algebras. But if you consider binary Lie algebras, then its free base unknown. So that's open problem, open question, and that's too difficult question, in my opinion. So to construct. And it's the same thing we have for Leibniz algebras. We know that the base of free Leibniz algebra, that is just left normed elements. That's again proved by Wadey. But if you consider again binary Leibniz algebra, free base, it's again unknown. The same thing for Zimbiel. Zimbiel, again, that is again left normed elements. But again, for binary Zimbiel, the base is unknown. And the same thing for binary associative, which is alternative algebras. The base is unknown. So we can see that in the binary case, to find basis, it's difficult. So we don't have so good example where the base of binary algebra is known, is constructed. Now, motivation for my problem. So let AX be a free algebra of the corresponding variety of algebra A. So we just fix the variety of algebra A, and we denote by AX its free algebra of this variety. And we denote by A minus the class of subalgebras of A under commutator. So again, in this talk, I started from associative algebras. If we take instead of A the variety of associative algebras, then Poincare-Birkhoff theorem provides the embedding of any Lie algebra into appropriate associative algebra under commutator. So as a consequence, we have the following quality. But in the case of alternative algebra, there is no exact answer. There is only known that a subalgebra of alternative algebra under commutator is a Malcev. So it's satisfied to the Malcev identity, of course. But the complete list of identities are again unknown. So for all varieties, we have the following diagram. Again, we have a variety of associative algebras, which is subvariety of the variety of alternative algebras. And we have minus is the Lie, here a Malcev. Lie is subvariety of Malcev. But here we have a full, here in the left side of this diagram, we have a complete answer regarding to the defining identities of under commutator, and the base of associative algebra is well known. But if you consider the right side of this diagram, we don't know anything about problems of free basis of the free algebra, and the complete list of this subalgebra, and we don't know free basis of Malcev algebra. So we don't have any answer here. So what can we do? For this reason, we consider well-known subvariety of the variety of associative algebras. So I take a subvariety of associative algebras, which is called perm. Perm, that's again well-known algebra in the theory of operands. That's known also. It's a lot of this algebra I would consider it with Wadey-Valette, and also this algebra given in the Encyclopedia of Algebras. And relative to perm algebra, we construct similar diagram for the considered variety. So about recent result of perm algebra, in the first work that's proved by me and Mashurov, we proved that every Metablian Lie algebra can be embedded into appropriate perm algebra under commutator. So in other words, it means that if we take subalgebra of perm, we obtain Metablian Lie, and we have analogical result that any Metablian Lie can be embedded into perm algebra. And also we constructed the way how to embed it in explicit way. As a consequence, we have the following result. Perm minus is mutable in Lie, where a perm that is a that's variety of perm algebras, mutable M Lie, that's a variety of mutable and Lie algebras. So here we constructed the following diagram, and now for the perm we construct analogical diagram. So that is this perm under commutator that's mutable in Lie, and now we take binary, the variety of binary perm algebras, and it's sorry, and it's and we consider its subalgebra under commutator. As I said before, for the right side of this diagram, we don't have results or about on free basis and the complete list of identities and so on. So we try to answer to the same question here. So in other words, we will try to construct free basis of the free binary perm algebra, and we will try to describe complete list of identities for subalgebra of binary perm algebra. So that is our motivation. So our motivation can be presented by the following diagram. So as I said before, perm that is a subvariety of associative algebra. So binary associative is the alternative. Under commutator associative is a Lie, and the under commutator alternative is a Malcev, but maybe here we have additional identities, but Lie is a subvariety of Malcev. And here we make the same thing, and we have the following connection. So now, before I just told you about what is a perm, I just told about you main objects, and now I will give you main definitions, what is perm algebra and so on. Oh, sorry. So an associative algebra is called perm if it's satisfied to the following additional identity. So what is this identity? That is the identity is called by right commutative identity. Why? Because as you see, we can replace elements, second and the third element that stay from the right side. And let me introduce the next main object of this talk. Now, guys, I just take some variety of algebra. So I just defined one variety of algebra V. Let V be a variety of algebra which is defined by the following three identities. So that I just take up some variety, this variety which is defined by these three identities. As you see, the first two identities, that is the first identity is a identity of right alternative algebra, that is of left alternative algebra, and also I add the third this identity. Oh, I forgot to tell you this bracket that is a associators. So we add the third identity and we call it by V. Now we denote by P and the Px the variety of perm algebras. So that is this, and the free perm algebra. Note that, so we can notice that this P is a subvariety of V. Why? Because and if P2 is a variety of binary perm algebra, then we have the following inclusions. So firstly, we have a variety of perm algebra, then we have a variety of binary perm algebras, and here we have a variety of algebras that we define here. So our aim here to show that we have equality between binary perm algebras and the V. We will show it later that these two varieties are equal to each other. Now we have that just these inclusions. To prove it, we use, of course, the basis of perm algebra. We use basis of this algebra, free algebra, of course. Free algebra, which is taken from this variety. Sorry. The basis of free perm algebra can be defined by the set of the monomials of the following form. So the set A, oh, sorry, before I wrote that A is a variety. Sorry, I used it one notion 2 times. So that is just set. That's another A. We take the set of these monomials. So the first element is a fixed, and we order all elements that stay on the right side from the first element. So we fix leftmost element, and we order remain other generators. And so that is the basis of the, if we take the set of these elements, so that is the base of free perm algebra. So it's not difficult to prove. Why? Because let me remind you that is we have associative identity, and also using this right commutative identity, so we can order them. Just fix leftmost element. So just one remark: dimension of multilinear part of free perm algebra, it's equal to n. So just again, we just fix this part. Here x1 and all elements are ordered and so on. Now lemma, and we use the following lemma. The following identities hold in Vx, so Vx algebra. Let me remind you, what is the Vx algebra? That is a free algebra defined by these identities. Identities for alternative algebra and this additional one. As you see, in alternative algebra, we don't have such beautiful identities. Why I call them beautiful? Because we have equality of monomials. As you see, defining conditions of identities of algebra V, we have equality of 4 monomials. We have here equality of again 4 monomials, and here again 4 monomials. If you work it with alternative algebras, so it's very difficult object. But if you will add the following identity, then we obtain such a beautiful identities, because as you see, these identities allow us, for example, identity 4 and identity 5 allow us rewrite any monomial as a left normal, as a sum of left normal monomials. Because what? Because you can see this monomial can be helped to write by this way, and also you can also this identity 5 also helps to write any monomials as a left normal. And oh, sorry, not 5, 6. I mean 6. Sorry, 6 and the 8. 4, 6, and the 8, as you see. So if you have this form, if you have identity of this form, and the identity 5 and the identity 7, they help to order all monomials which stay from the on the right side relative to the leftmost element. So we see BCD, CDB, DBC, and the same thing with the for in degree 5. How we can prove it? So just use some programs as a as example. You can use program Albert, maybe Haskell also can help to prove it. So all programs show that these all identities holds in Vx. So now let me fix the following sets. So for the alphabet X, X1, X2, Xk, we define the set. We define sets B1, B2, B3, B4 as follows. So B1, that so this index 1, 2, 3, 4, it means that is the length of monomials. So here it's just letter. B2, that is all possible pairs. B3 and B4, we have this following index with this order. And starting from degree 5, we define Bn as follows. If starting from degree 5, that is the left normed monomials where all indexes are fixed. Sorry, ordered. Starting I2, I3, In. So and this In we can order, so they are ordered. Starting from degree 5. So theorem, the following set is the basis of Vx algebra. So, so how to prove it? So just use these lemmas, as I said before. Just use this lemma, these identities, and we can prove it using whole method. Just construct multiplication table for this algebra Vx, or we can do in the other way. How to prove it? We can use basis of the perm algebra. As I said before, we have the following inclusion. The dimension of P multilinear part of free algebra of the perm algebra, it's equal to n. And here, starting from degree 5, it's also equal to multilinear part, of course, also equal to n. But from this inclusion, we know that the dimension of this algebra, of this algebra Px, that is the varieties. But here I just saying about free algebra. The dimension of this, of the free algebra from this variety, oh sorry, the dimension of algebra from variety V, free algebra, cannot be less than the dimension of free algebra variety perm. But we know that here, starting from degree here in this, it's equal to n multilinear part. Here, starting from degree 5, also equal to n. So it means that that is the basis of algebra V. Oh, that is just short way how to prove it. And as a corollary, we have the following: P2 is equal to V. So in other words, the defining identities of binary perm algebra, that is this, sorry, that is these three identities. Again, how to prove it? We know that binary perm algebra, it contained in V, and we have to show inverse the following inclusion, that V is contained in P2. In other words, it means that all identities of P2 hold in V. So by straightforward calculations, one can be obtained that all identities of degree 4 of binary perm algebra follows from defined identities of V. And as I said before, starting from degree 5, the dimension and the basis of algebras Px and the Vx are the same. And since we have the following inclusion, the dimension of basis and the basis of P2x binary perm x from degree 5 also the same with this Vx. So because it stays between them. So all identities of binary perm algebras falls from 1 to 3. Finally, we have the equality, this equality. So, oh, sorry. Oh, okay. So we achieved our first aim. What we do, we define it. What we again, we find the defining identities of the variety perm algebras, and moreover, we constructed the free basis of the free binary perm algebra. Now, let me answer to the question about subalgebra of binary perm algebra under commutator. So, as I said, we consider algebra binary perm minus, which is subalgebra of binary perm under commutator. Since binary perm is a subvariety, so we know that binary perm is a subvariety of alternative algebra. We have the following inclusion. Subalgebra of binary perm algebra. Binary perm minus, let me call just minus, not commutator, so on, just binary perm minus. So binary perm minus, it's we have it's contained in alternative means, and we know it's well known that alternative means contained in Malcev. So here we don't have any information about free bases or base. Here we don't have again don't have any information, and for this reason we will try to answer here for the same problems. Also, I said the same thing. The problem of finding complete list of identities is still open question, open problem. Also, the bias of valid unknown. For this reason, we describe the complete list of identities of binary pair minus, and moreover, we construct the basis of this algebra. So, theorem. So we know that binary pair means it's anti-commutative. We have anti-commutative identity. So anti-commutative algebra binary pair means satisfies the following identities: 9, 10, 11, 12. So what we see here. So identity 9, it helps identity 9 and the 10. These two identities help to rewrite any monomial as a left normal. Of course, using also with anti-commutative identity, just not these two, and also using anti-commutative identity. And identities 11 and 12. So these are identities, firstly, 11 and 12, they help what they can do. They help to order these three generators, C, D, E. They help to order these three generators. And also we have Jacobian and the DE, it's equal to 0. This identity, it helps to order all generators starting from that stay from the right side on the from leftmost element. And we have the following theorem: all identities of binary pair algebra minus are consequence of anti-commutative 9, 10, 11, 12. So we answer to the question about complete list of identities. So that is this 5. And now we have to check these identities to independence. It means that maybe we can remove the identity so it means that some identities can be it can be consequence, so we can remove it from this list. So we have the following theorem: the identities 11 and 12 are consequence of anti-commutative identity and the identity 9 and 10. So in other words, we just need 3 identities here. 11 and 12 12's identity can be removed from this list. And we have the following. Again, the anti-commutative identity and the identities 9 and 10 are linearly independent. How we can prove this again? As before, we can use Albert or Haskell. So just use these programs and they will show that these identities are linearly independent. This program is good to work for low dimensional so for monomials starting from up to degree 7, but starting from degree 7, it can't answer, of course, to this question. So we could just can use this program for low degrees. Now, let us define the set of monomials Cn as follows. So Cn, that is the monomials of this form. So which satisfy to the following conditions. So we just fix leftmost element, and all other index generators can be ordered. So this set of monomials, it looks like a basis. It's not looks like it's so the set of these monomials, that is basis of metabolin Lie algebra, as you know. And also this set of monomials is the basis of P2 minus algebra. Of course, starting from degree 5. So again, starting from degree 5, the basis of this algebra are monomials, this set of monomials. If you ask about monomials of degree 1, 2, 3, 4, so in degree 1, 2, 3, that is just monomials of anti-commutative algebra, and in degree 4, just calculate base from with these two identities. But starting from degree 5, we have general answer. So we answered to this question completely answered to this question. Now, what about let me think. What about binary perm plus algebra? So what about binary plus algebra? It's well known that alternative algebra, so plus it means that anti-commutator. So instead of minus, we just consider AB plus BI. So it was noting that binary perm plus algebra as alternative plus is a Jordan algebra. So it's well known that perm algebra under anti-commutator consists with the Jordan algebra with additional identity of the following form. So that is the perm algebra. And by direct calculation, one can prove that binary perm algebra under commutator also is a Jordan we also satisfy to the identity 13, which means that this binary perm algebra under anti-commutator consists with the Jordan algebra with identity 13. So this result is not new; it's not known result. I see I have time, so I will show you another result. If you allow me, I will show you another results regarding to perm algebra. I didn't add it to these slides. I thought that maybe I will speak. I will not have enough time, but I see that I have time, so I will show you another result.
Yeah. So
What?
you still have 22 minutes.
Oh, let me just show you the last results. So, and I will finish with this. And okay. Now I will consider, before we consider what we considered, we considered perm algebra under commutator, and then now we consider NAP algebra under commutator. What is a NAP algebra? Firstly, let me explain. NAP, it is a non-associative permutative algebra. So in other words, in perm algebra, we forget associative identity, and it just remain right commutative identity. So what is the basis of NAP algebra? No, let me remind you. That is a well-known result. I mean about this algebra also considered by Wadey, I forgot, maybe Valette. Okay. So free NAP algebra was considered in 18. That is Wadey's work, which stated as follows. Let's take the set X, and of course that is generators, and the generators are ordered as follows. So just by index. And for given non-associative monomials, and we take two arbitrary non-associative monomials U and V from NAP algebra, and we write U less than V if one of the following conditions hold. So in other words, now we define order on monomials of NAP algebra. So firstly, we define by degrees of U and V. So if their degrees are equal, then we just take, then we know that non-associative monomials can be written as a U1 multiplied U2, V also V1, U2. And we consider them as lexicographically. So we firstly consider from the monomials of the left side. If they're equal, then we consider monomials that stay on the right side. So that's such order is called Deglex. Let be a set of monomials of the following form. So we take monomials of the following form here, sorry, here. Sorry. Okay, here xi is just generator. It can be arbitrary generator, and W1, W2, and so on, Wn, that is a non-associative monomials, which is ordered as follows. Of course, by relative to the Deglex order. Such a set is the basis of free non-associative permutative algebra. So this set is the basis of NAP algebra. That is a result again. Maybe Segal. Yeah. So that is a because the same basis also constructed to left symmetric algebra. Sorry, right symmetric algebra, and this result also can be used for so NAP algebra. Now we have the following theorem. The algebra NAP under commutator satisfy only anti-commutative identity. So let me remind you, perm algebra under anti-commutator, we have it's so under anti-commutator, it's so rich class, rich to the identities, because we have here Jacobian, we have Metablian, but if you forget about associative, we don't have anything here. If we have just right commutative without associativity, we have only anti-commutative identity. So how to prove it? It's not difficult. Just it's sufficient to show that anti-commutative identity it's isomorphic to NAP minus. So we just use the theory of Grobner-Shishov base to show this isomorphism. That's not difficult. So if you consider again, and if you consider a NAP algebra under anti-commutator, before we consider under commutator, it's also satisfy only commutative identity, and the proof is the same as the proof for the commutator in the commutator case also work for theorem 6 for the case of anti-commutator. So let me make again one remark. This result, I mean that NAP plus is just commutative, is proved by Wadey in work not 18, not this work. Oh, but here in this work we just give a short proof of the Wadey result, but he didn't have the following theorem. We prove it that is a new result, but this result is the result of what they. So I think that's all. I said all what I want. So if you have any questions about unary binary algebras.
Okay, thank you very much. Are there any questions?
So again, let me again tell
there is
something.
A question on the chat.
Sorry.
Nikita. Okay, please give a relevant example of perm algebra.
examples of perm algebras. Okay. So explicit example of perm algebra. I know just application of perm algebras. So let me tell you about maybe application, because now I can tell you examples. For example, about application, in apparat theory, we know these things, white money product, and the perm algebras, it helps to find, it helps to find, it helps to define the algebras. So if we take variety, any variety, if we take any quadratic apparat and multiply to its white money product to the perm, then we always obtain its the algebra version. So that's its application. And also we have algebras. So for example, from Lie we can obtain pre-Lie algebra. Sometimes it's called right symmetry. So if we multiply perm algebra to black money product to some fixed variety, we always obtain pre version of the fixed variety. So that is just application in operant theory. But explicit definition of some examples, I didn't thought about that. So
But for example, any commutative associative algebra is a perm algebra, no?
Yes, that is a trivial example,
Yes.
maybe, but but I thought about something maybe for someone this answer it's not to be satisfying, because associative commutative, that is well known, so maybe they're asking about non-trivial examples. But now I can't answer to this question.
Yes, there are some other questions. Another question by Florin Nikita and by Ivan Tagorodov. Ivan is asking what you can say about mono perm algebras.
Oh, monoper. That's a good question. I thought about this question before this because before this seminar about mono perm algebra. So as I said before, main motivation here was as I said before, so alternative algebra. So that is we have a lot of unanswered problems here. So for alternative, and for this reason, I consider here a binary perm. But if I will consider mono perm, then there is no any relation with alternative. There is no relation with alternative. But I can tell you something about by mono perm. So we know that mono associative algebra is a power associative. So it means that it will be something subvariety of power associative. So I just have hypothesis. I didn't check it. Maybe it's not difficult, but it's power associative algebra with one additional identity of degree 4, maybe 5. But so it's not. It didn't was. It didn't. It's not interesting because it's didn't have any connection with the alternative.
Okay, there is another question by Florin Nikita. You probably can read it by the chat. Oh, he's asking.
Sorry, what?
Yes, there is another question by Florin Nikita in the chat. What could you say about this? The condition is quoted in the chat. Is similar to the Jacobi identity by using associators. A, B, C plus B, say A plus C, A, B equals to 0.
Sorry, I didn't get your question. Can you repeat, please?
Read it by yourself in the chat.
In the chat. Oh, okay, in the chat. What could you say about this one? Oh, I see. What could you say about this one? That is associators. So what can I say? So maybe this identity also hold in this binary perm, but I'm not sure. But if you want, I can check it. It's not difficult to check, but not now. I can't tell anything about that. So I don't know the meaning of this identity now. That is so. That is ABC. So I see that is just you are so that is just you just replace ABC, BCA, C as a that is a Jacobian, but relative to associator. But I don't know now. I don't know the meaning of this identity.
Okay. Are there any other questions, comments, or remarks? Okay, if not, let's thank the speaker again. And we will resume on next Monday at the usual time. Bye, everybody.
Okay, thanks again for invitation and for listening me.
You're welcome.